Hello everybody, welcome to this presentation of a novel two-dimensional non-stationary wideband massive MIMO channel model. My name is Carlos Lopez and this presentation is part of the 5G wireless project aimed to create innovative architectures, wireless technologies and tools for high capacity and sustainable 5G ultra-dense cellular networks. In this presentation, I will briefly introduce some of the most important massive MIMO channel characteristics and recent advances on channel modeling for massive MIMO, along with the limitations. Later, I will introduce the model we have recently developed to overcome some of these limitations, and finally, I will draw some conclusions about the channel model and future work.
Using large arrays composed by many antennas has resulted in new channel characteristics. These are some of the most important, and I will focus on the first two in the following slides, that is, the near-field effects and the environment evolution. Increasing the number of antennas without reducing the space between them to avoid increasing correlation between channels make these arrays considerably large. This results in what has been called near-field effects, that is, the array is so large that many objects or users lie within the Fresnel region of the antenna. I have included an example with a uniform linear array composed of 100 antennas, spaced half wavelength at 2 GHz. The array will be about 7 meters long, and its far-field region will start at 750 meters away from the array. As you can imagine, in a city there will be many things closer like buildings, cars, mobile stations, etc. Near-field effects can be better understood by looking at the figure on the left, which is an abstraction of the channel. There you can see how scattered or direct signals reach every antenna element at different angles, delays, power, etc. That is, these channel properties are not constant along the array. The figure on the right shows the angular power spectrum of a 128 element array. The y-axis represents the angle of arrival, and the x-axis the position of the array with the received power in color. You can see that there are changes in the angle and amplitude of these multiple components along the array. The second major effect is what could be called environment evolution. This is related to the fact that some scatterers or users are not visible for the whole array. Some scatterers get occluded by others, and this could be seen as variations of the environment for different antennas along the array. On the right, you can see the received power along the array for different users in color in both line of sight and non-line of sight conditions. You can see variations of the received power about 4 or 5 dB along the array. Also, since every antenna receives signals from a different set of objects of the environment or clusters, there are different delay spread, Doppler spread, and other characteristics for every antenna. Recent advances in channel modeling have included spherical wavefronts to improve the accuracy of the results and modeling some of the effects mentioned. However, spherical wavefronts are theoretically difficult to deal with and computationally expensive compared to planar. Even though the spherical wavefront leads to non-stationarity of the array, they require new information about this environment, such as the distance to objects, and the expressions are usually less insightful. Above you can see an example of the expression required when the spherical wavefront is used. This expression represents the distance between one element of a uniform linear array and a scatter n. Below, the common expression for the same distance when the far-field assumption is used. It is easy to see that it's just a first-order approximation of the first, leading to plain wavefronts. In regard to environment evolution and focusing on clusters, recent models include two different approaches. First, the so-called cluster appearance and disappearance through a Markov birth and death process. In this approach, clusters of constant power appear and disappear suddenly from one antenna to the following. The second approach includes what has been called visibility regions, a concept inherited from cost models in which every cluster has a region in space where it's visible. In this approach, a linear variation of the cluster power has been considered by introducing a visibility gain. While the second approach uses smooth variations of the cluster power, both approaches show evident limitations in modeling cluster evolution of the array. Now, let's see what massive MIMO measurements show with respect to the effects already mentioned. You can see here more examples of measurements of the angular power spectrum and its variations on the array. there are some aspects in common among these figures, and one of them is that many multipath components, or clusters in the angular domain, present linear variations, or almost linear variations of the angle along the array. There are exceptions, but they are low-powered and rare. Since these variations are a consequence of the wavefront, it might be enough considering wavefronts leading to linear variations only, and thus reducing the complexity of the model. Here, you can see some examples of cluster average power along the array in the upper figures. The x-axis represents the antenna index or position, and the y-axis the power of the cluster, with different clusters in color. There are clusters that appear and disappear, but there is also a power variation that recalls shadow fading. Below, these figures represent not cluster but the total power variations on the array for different users and conditions. Here, cluster disappearance cannot be observed, but the resulting power varies in a similar way. Last figure represents the recent K factor for different users in line of sight and non-line of sight situations. It's quite variable along the array as well. Based on these measurements, cluster disappearance or linear visibility gains seem two simple approaches to model cluster evolution. Now, let's introduce the new geometry-based stochastic channel model proposed. As I said, the motivations for developing an improved channel model are that spherical wavefronts are too complex and cluster evolution is too simple in current models. The new approach I propose requires using parabolic wavefronts, that is, a second-order approximation to spherical wavefronts leading to linear variations of the angle of multipath components on the array. Secondly, an individual cluster evolution process, including cluster reappearance, through a Markov two-state chain and smooth variations of the cluster average power through a log-normal solving process. This wavefront is a parabolic or second-order approximation to a spherical one. Here it's represented a large uniform linear array and a cluster described by its cylindrical coordinates r alpha. The normalized distance from the object to an antenna in the array rp over r is the one indicated under a spherical. It is represented as a function of the normalized distance as well, for clarity. This distance from the object to an antenna can be approximated by the first or second order polynomial leading to plane or parabolic wavefronts, respectively. The figure on the right shows this normalized distance for different angles. The horizontal axis is z, the normalized position on the array, and the y-axis is the distance from the object to such position on the array. You can see that for a large array, the first order approximation is not suitable, but the second order approximation is quite good for most angles. Second, the approach presented here to improve previous models considers cluster reappearance and smooth power variations on the array. You can see a similar scheme, but in this case we introduce objects that can obstruct or attenuate the signal. For the obstructions such as the house represented in the figure, a Markov two-state chain process is used for every cluster, taking values 1 or 0 depending on the cluster visibility. To model power variations on the array, a log-normal space process is used in a similar way as shadow fading is usually modeled in mobile communications. The resulting process is the product of these two, showing both cluster reappearance and smooth cluster evolution. The received power for every element on the array could be calculated easily as indicated in the figure. Here you can see the most relevant expressions of the channel impulse response of this model. We have the line of sight and cluster power for every element of the array expressed as we have already seen, and the parabolic wavefronts indicated here in the face of the line of sight and cluster components. Here we have an illustration of what could be the cluster evolution in previous models. The x-axis represents every antenna in the array, and the y-axis the cluster index. Clusters appear and disappear along the array suddenly without power changes. And this is what results when you introduce power variations for every cluster. The normalized power is represented in color, and you can see cluster reappearance and smooth power variations. Looking at individual clusters from a different perspective, we can see the cluster power evolution in this way as well. Here we see cluster disappearance and power variations on the array. On the right, it's represented total power along the array for different variants of the cluster power, leading to a higher dynamic range of the power. Below, the K factor in the same conditions as above, it is quite similar to what we have seen before in real measurements. Since the channel is non-stationary in the array domain, the space cross-correlation function must show this effect by depending on the antenna position, and not only on antenna difference. As you can see on the left, the cluster-level space cross-correlation function depends on the distance between the antennas and the position of the antenna itself, so it shows non-stationarity. On the right, the angular power spectrum shows linear variations of the angles of multipath components and smooth variations of the cluster average power as expected. Also, some clusters appear, disappear, and reappear as well. Finally, let's see what conclusions can be drawn from this research work. As we've seen during this presentation, improvements of state-of-the-art channel models have been made, including parabolic wavefronts, cluster reappearance, and cluster power evolution. The parabolic wavefronts are able to model linear angular drifts on the array of massive MIMO channels, and the Markov-Berdendieff process and the log-normal cluster shadowing process are able to represent the cluster reappearance and smooth power variations of the clusters. In terms of complexity, accuracy, and flexibility of the model, on the one hand, the state-of-the-art channel models are slightly more accurate, more complex, and slightly more flexible in practical situations than the proposed channel models in terms of the wavefront. On the other hand, in terms of cluster evolution, the conclusions are the opposite, since the proposed model is more accurate, complex, and flexible. You can find more information and details of this work in the proceedings of the International Workshop on Computer-Aided Modeling and Design of Communication Links and Networks this year. In the future, regarding the channel model developed, we are interested in analyzing the impact of parabolic wavefronts and smooth cluster evolution approach on other metrics like capacity. Also, we need to carry out measurements to obtain parameters of the proposed model and other new characteristics ignored so far. Moreover, extending the channel model to 3 dimensions is of great interest and importance for specific environments. Finally, a comparison of the model with the state-of-the-art channel models will be also of great interest. These are some references used for this presentation regarding the measurements and models for MassiveMIMO wireless communications. Well, that's all from my side. Thank you for your attention, and if you want more information about the 5U wireless project, don't forget to subscribe to our YouTube channel, visit the project website, and follow us on Twitter. Thank you.